So in this topic, we'll talk about the conservation of momentum. Before we work on conservation of momentum, let's fix some ideas here in space. First of all, let's consider a small particle or fluid particle in 3 dimensions, obviously. And let's suppose that fluid particle is actually moving along. And that particle is going to have, you can express this particle in a Cartesian coordinates in the XYZ direction. If you can do that, then you can show that the shear stresses and the stresses acting on this box look like this. Okay, so and on the opposite side, you will also have that. So when I'm saying this, if I look this way from the z direction, what I am saying is what you're gonna have is you're gonna have this, you're gonna have this. That is your tau xy. They have to be symmetric, by the way. Then you're gonna have this. I'm gonna call this sigma xx. You're gonna have this. I'm gonna call this sigma yy, but you're gonna have it equally opposite on the opposite side. So you're gonna have this. You're gonna have this, this, and this. It has to be completely symmetric. Okay, so that's important. And then for each one of these surfaces, we can have a resultant vector. Vector resultant, let's call that t. Okay, t that's acting, let's say, in the y plane, right? And then the t acting on the y plane will be tau xy in the I direction. So it goes, this one goes in the I direction. Remember, these are symmetric, so that's why I write them like this. Plus sigma yy in the j direction, plus tau yz in the k direction. Okay, and then on this plane here, you're going to have a resultant stress vector that will actually is actually equal to sigma xx in the I direction, x direction. This is in the z direction. This is in the y direction. So this is tau xy in the y direction plus tau xz in the k direction. And then here you have another resultant, and that resultant will be in the z plane. So that's what we call it z. And that would be sigma zz. Oh, wait, let's start with x. So this is tau xz in the I direction plus tau yz in the k in the j direction. So this would be this one right here plus sigma zz in the k direction. So these are my stress vectors, the total stress vectors acting on that particle. That's important as we go along, as we derive the equations for momentum now. Now, the conservation of momentum, we're going to divide this talk in 2 parts. The first one will be for a fluid particle. Okay, and for the fluid particle, so we know that for a particle, if you remember from physics, that the rate of change for momentum, so rate of change of momentum is going to equal to dm dt summation of forces in m in total summation of forces. Now, what you have to know that here let's write it down here. This is nothing else than a small change in moment, in mass, sorry, times velocity, and that is given, that's known as the momentum. F is the total force acting. Um, this is the force acting on that particle. And then delta M will be the small incremental mass. And delta V is going to be this small incremental volume. Okay, so now let's see what happens with each one of this part. Let's work with part 1 on this side. Let's work with part 2 on the right hand side. So this side, on this side, the substantial derivative of momentum is nothing else than take the total derivative of my delta m times velocity. Okay, and that will give you a delta m times velocity, and delta m is nothing else than rho times delta volume. Okay, it's a change in the volume. So I could express this whole thing as follows. Delta t rho delta v times velocity. And that would be, now let's use the chain rule for each one of these terms. And that will give you uh, velocity times delta t times rho delta v plus rho delta, delta v times dv. Okay, so for a particle, for a small particle, this term will be 0 for particle. Why is it 0? Because it's so small, and the time, and so that since it's small, the volume will be, is basically not going to change with time. So what we can say safely is that dt of delta m will be 0. Okay, so this is what it looks like for the first part. So in other words, the left hand side is actually equal to rho times delta v, derivative of velocity respect to t. And now just note and remember that this from our previous discussion is substantial derivative. So this is actually equal to the partial derivative of velocity respect to time plus the gradient plus, velocity dot times the velocity. Okay, and you can also further show that this particular part, we can expand it, and this expression becomes very convenient later. You can write this as follows, where this is v, v. This is the curl of v. So this becomes kind of convenient. Remember, this is nothing else than the curl of v. So that means that the whole expression, I could write it as follows. This is for a fluid particle. Minus v, and I'm going to write it curl of v. Okay? So this is your left-hand side. Now let's work on your right-hand side and see what your forces are. Okay, this is your item 1. So now we're going to go on the right-hand side and expand what the forces are in your problem. So the forces, let's say number 2, the summation of forces is going to equal to the body force, and I'm going to explain that in a minute, plus pressure forces, plus viscous forces. Okay, so to understand this, let's call this item A, let's call this item B, and let's call this item C. And we're going to expand each one of them individually and see what they really look like and what they are about. Okay, so item A, these are body forces. Okay, and the body forces that we typically consider in a fluid typically are gravity, and then so in that sense your body will actually equal to delta m times F, okay, where this is nothing else than F. It's actually equal to rho times delta B. Okay, so in this expression, the way we're going to express this, this is nothing else than the body force by unit mass. This is how this is expressed in this term. So this is important because then that means that in this expression, if I'm working only in gravity, this is nothing else than acceleration, right? Like gravitational acceleration. So it will, if it's only applying in the vertical direction, that's the only way you're going to have a body force, right? If it's going downwards, then you have a G. Let's say I have a coordinate system that goes like this, where this is Z, I'm sorry, this is X, this is Y, this is Z. So then this will be going, let's say, in the J direction, and it's minus because going downwards. Only under this case, so this whole body force will actually equal to minus G times I, as an example, right? I'm sorry, this is F. Now, normal acceleration does not constitute a body force. It's only gravitational. So if I have a fluid that's actually moving in this direction, in the x direction, according to this plot I have here, then you know that your body force is equal to 0. Why? Because if really I can assume that there's very little effect happening on my particle as it's moving along this direction. However, if it's moving up and down, it's just free falling, if you would. In that case, this will not be 0 and has to be considered. Okay, for most of our problems, we will be able to assume that that's actually equal to 0. Okay, so the second term that we work is the pressure. Okay, and to work with the pressure, so we are working on F pressure. Many times, a different textbook like to call this the force on the surface. It's all the same, right? This is the pressures acting on the surface. So just to better understand this, let me go back to, if you remember this, right, segment, and let me go and look from, I'm going to look from this side, okay? And let's see what happens here. So I'm going to take this, and let's take this coordinate system, X. So the unit vector is I. Let's go into Y. The unit vector is J. And let's use K for your in the Z direction. So if I was going to just look at this, looking from this side, and I have a particle, it's a very small particle. Remember, it's just a small element of the whole fluid. From the whole fluid, I'm taking a very small, tiny particle that actually a small cube from that I'm analyzing it. I have a middle point B, P. I could actually express it. A better drawing probably looks like this. Okay, probably this is a much better drawing in 3 dimensions. So what you're going to have is you're going to have a pressure acting on that point. That's a pressure. But then halfway on this direction, you're going to have half of that pressure. You're going to have some differential because this is a element that can expand or it can contract. So this is going to represent the expansion or the contraction on either one of the sides. Obviously, if this is going in this direction, this is going in the opposite direction. So this side, on this side, this is minus y. If you consider this half of it, so anything on this side is minus dy, anything on this side is plus dy, okay, over 2, sorry. So that's why we got the plus and minuses. Okay, so basically the total volume in this in over this cube will be dx, dy, dz, sorry, delta volume, so this is delta v. So you have delta y, delta z, okay? And then rho will be your density. So do you have, and this is the volume, and then you have the density. This is volume, and you have density. Okay? So to add the forces, remember you have to add the area. So you have delta x and you have delta z. So all these terms have to be multiplied by delta x and delta z. So I have to multiply this area where this is acting, and I need to multiply this area where this is acting. So if I did that, I'm going to do it only in one direction. Let's call this pressure in the y direction. I can have minus p partial of p respect to y, delta y over 2 dx dz. So this is acting in this direction. This is acting in the opposite direction. Then will be a minus p, sorry, this is a p minus. This is p plus partial of p with respect to y, delta y over 2. So sorry, delta x, delta z, delta x, delta z in the j direction. So you can simplify the whole thing, and I will let you do the math and show that at the end of the day, the result that you get is partial of p respect to y in j, and you get delta x, delta y, delta z. All this is nothing else than a delta v. So this comes from the fact this is my volume, and then this whole thing actually equals to minus partial of p respect to y in j delta v. Now you can show that this is all in the y direction. Similarly, you're going to have pressure in all other directions, right? So your pressure in the x direction will be minus partial of p respect to x in the I direction, delta V, and your P in the Z direction will be minus partial of P respect to Z in the K direction, delta V. Okay, so at the end of the day, you can express this whole thing in a very simplified manner and call this pressure will be equal to minus P over delta V. This is the gradient of V over delta V. Okay, so this is the total expression for the pressure in the most general case. Just as a reminder, don't forget that this is in Cartesian coordinates. This is actually a vector. So that's why you actually get a vectorial. You get a vectorial notation. So now we are done with the part A, part B. Let's go to C, the viscous part. Okay, viscous part is important because remember your fluid is going to be hitting a wall, so it can have viscosity, right? It can have friction, and the friction is what brings the viscosity into place. So this is equal to viscous. And I really don't want to spend too much time deriving all of this, but let me just give you, in a nutshell, what we are really trying to capture and do here. Um, so in here, what you have to keep in mind is that this is delta, this is delta z, this is delta, this is delta. Okay, so what we are basically trying to do in this case, if I add in this direction, right, everything in this direction, you're going to see I'm going to add what the viscosity is here, the viscosity is here, and there, and there, and there. Okay, so at the end of the day, you can show, and I'm going to skip some steps here. You can show that the results that you're going to get are following. So you can show that the viscosity in each one of the directions, let's say viscosity in the y direction, I'm going to get, this is uh, partial of tau xy of x plus partial sigma yy of y plus partial sigma of z respect to tau yz, and this is all in the j direction, and this is delta volume. Okay, and you can show the same thing you get for every other, for the other uh, for the other segments as well. Okay, so if I combine all the terms now, uh, you will end up with the following expression. Let me go to the next page. Rho, total derivative of your velocity respect to time, is going to equal to your body force times rho minus your gradient of pressure plus your effects of viscosity. And then what I'm going to express here is this is nothing else than the gradient of t of x in the I direction plus the gradient of t of y in the j direction plus the gradient in z in the k direction. Okay, remember your t, I defined these t's here at the beginning, right? So let me just expand one. Let's take this one, right, for an example. So if I take this one and you have partial of x, I, plus partial of y, j, plus partial of z, k, you're taking the dot product with sigma xxi plus tau xyj plus tau xzk. Okay, again, this comes from here. The x term is right here. So if we take the dot product, you find that that's actually equal to partial of sigma xx respect to x plus partial of tau xy respect to y x plus partial of tau xz respect to z. And that's just for this term. And you can do it for the second term and the third term and show that this is how you will actually do it. Okay? So another thing you have to remember, just want to point this out here, that on this left-hand side, this expression right here, we show that this was actually the partial of v respect to t plus v squared over 2 minus v times curl of v. Okay, or nothing else than this times cross product this. Okay, so there's an L missing there. So this is everything happening in the particle system. Now for the fluid system, okay, now I'm going to work with the whole fluid. Here I was working what happens if I stand at the particle, right, and see what's happening. Now I got a fluid, I got a particle right there, and I'm working with the fluid system. Okay, so we call it FS for fluid system. Okay, so if that was the case, I'm going to skip a great part of the derivation and just give you the answer for this. So what you have is the total surface, the force acting on the surface is going to equal to the force acting, is basically the same as the pressure. And we show that that's actually equal to minus P delta V, right? We show that. I showed you that previously. So what we can write in the integral form, that's what we use more typically, is as P ds. Just remember that this term right here is the same as saying that this is the vector S, where this is the surface area, right? So it's the enclosed area in which all this is acting. We're going to call it S. Okay? So the second part that we have here is F body. So that this would be the body force would be over the control volume, F rho the volume, and your viscosity would be the enclosed integral over the area over Tx dot times I plus Ty n j plus Tz n k. This is ds. And remember again, this x, y, tx, ty are given here. And one last, and just remember, this is the total, the left-hand side will actually equal to the derivative of r rho v, the volume. And this is very interesting. If you remember from our previous derivation, I told you that we could have this, we derived this equation in the previous class where you went here, and I told you what this will actually look like for Q times rho V, right? So in this case, your Q is equal to V, is a vector V. So you just have that expression, you know how it looks like. So the next is best just to do a couple of examples and to better understand how this works, and we'll do that in the next lecture.